All right, folks, so now we're in this last idea in chapter 7. We started off looking at enthalpy, entropy, Gibbs free energy, and kinetics, how fast reactions go and how they happen. This last idea we're calling equilibrium. And I want to give you some data here, some evidence to see what this looks like. So I want you to imagine I'm going to react sulfur dioxide with oxygen. So what I'm going to do is, here's my picture of a reaction vessel. Initially, I'm going to put SO2 gas and O2 gas in there. And then start the timer. And later, a minute, 2, 3, 4, I'm going to check the concentration inside the reaction vessel. Well, initially I've got SO2 and O2. That's all that's in there. But once the reaction starts to happen, I'm getting some SO3. So later I've got SO2, O2, and SO3. So initially, let them react. The reactants start to form the product. Now, what I've got is sensors that tell me the percent of the mixture. So initially, when I look at this thing, I'm trying to find a nice piece of paper here. Initially, 50% SO2, 50% O2, and there's no product, right? I put those in there and then hit a button. A minute later, I check. Now look, SO2 has dropped from half to 20%. O2's dropped from 50% to 40%. And look what happens to SO3. It's going up. Oh yeah, that makes sense. Those are reacting, dropping. That goes up. Minute 2. Oh yeah, SO2's down to 10%, 20% for O2. SO3's up to 70%. At minute 3, 3%, 7%. Take a minute and think about what that other number should be. Right. 90%. At minute 4, I'm down to 2% SO2. O2 is down to 5%. And SO3 now has jumped up to 93%. So you can see where this is going. What I'd like you to do is stop and say, okay, well, at minute 5, maybe minute 6, minute 7, what would you predict? SO2 went from half, it's dropping. O2 is reacting and dropping. SO3 is being produced, it's going to go up. So at minute 5, I go back to my sensors and I notice, okay, 2% SO2. Maybe that's just a rounding error. Maybe this was like 2.4 and this is 1.8. Okay, 2%. Well, this is certainly going to drop down to 3 or 4%. And I check that number and it's 5%. SO3, 93%. So I say the two words that we often say in lab, O, and the second word could be a variety of different options. But I think, okay, maybe something went wrong, some numbers got rounded, whatever. I'll check it again at minute 6. Certainly, the reactants will drop at minute 6 and SO3 will go up. I go and check everything, 2%, 5%, 93%. Something weird is happening here. It's like the reaction has stopped or something. Minute 7, 2%, 5%, 93%. So now I have to get out the red pen. What is going on here? Well, here's what's going on here. Here's what's going on here. Here's my data. Well, initially, I have 2SO2 plus O2 reacting. There doesn't seem to be anything wrong with that. They start reacting, those two start to drop, and SO3 starts to go up. Well, what's happening to these concentrations? As those get used up in that reaction vessel, their concentrations drop. SO2 drops 50%, 20%, 10%, O2, 50%, 40%, 20%. You say, oh yeah, those are dropping. Well, so what? What are the implications of that? The concentrations are decreasing. Now, the last thing we talked about was kinetics and rates of reaction. So if you think, well, if the concentrations of those are reacting, what's happening to that reaction rate? It's slowing down. That reaction, as the SO2 and the O2 keep getting used up, there are few of them bouncing into each other, few of them encountering each other, then that reaction slows and slows and slows. Okay, that's not a surprise. Here's the big surprise. Another reaction begins. We call it the reverse reaction. In almost every reaction, once the reactants start to make products, once these start to react to make this, this additionally starts to react or decompose, and the reactant or the products actually start to a reverse reaction. So this slows down and this starts to happen. There's almost always a possible reverse reaction. So that starts to happen. Well, what's happening to the concentration of this? Well, initially as I make more and more and more SO3, the concentration of the SO3 goes up. Well, then guess what? This gives me a faster reverse reaction. So this starts and begins to slow down. This starts and begins to speed up. Well, if I was in lecture, I usually do kind of a demo of, if you're like at an airport or something and they have those long people mover conveyor belt things. Well, of course, I always get on them, turn around, face backwards, and walk backwards on the conveyor belt. Well, think about that. You're rolling along, you're going forward. You turn around when you're on that people mover flat escalator thing and start walking. You can walk at a speed that basically you're not changing your position. You're not moving forward or backward. The conveyor belt speed is equal to this immature teacher walking backwards on that conveyor belt. And when that happens, I'm going to say 3. Eventually, after some amount of time, we get this condition called equilibrium. Sometimes we draw it like this, meaning there's a forward reaction happening and there's a reverse reaction happening. And what's really going on is the forward rate equals the reverse rate. So that's the case where you're standing on that people mover thing and you're walking backwards, walking in the opposite direction of the belt. You can do this at an escalator. I think we have one escalator in Chico. You can go to Penny's, and my daughter loves to do this. Get on the escalator going up, then turn around and start walking downstairs. You can get stuck between the two floors without moving. The escalator's going up, you're going down. The escalator's going up at some rate, you're going down at the same rate. You don't move. You just stand there and look over the watch section. Okay, when that happens, we call it equilibrium. Now here's what we notice. In the same way your position won't change on that escalator, the concentrations will not change. Concentrations do not change. Notice what happened up here. Oh, SO2, 2%, 2%, 2%, 5%, 5%, 5%, SO3, 93, 93, 93%. I notice, there's no change. Maybe the reaction has stopped. No. When you're on that escalator, and you're walking down and the escalator stopped, you haven't stopped and the escalator hasn't stopped, even though your position is not changing. So under this equilibrium condition, we would say the reactions are still happening. And just to be clear, we mean the forward reaction and the backwards reaction. They're still happening. It's just they're happening at the same speed. We don't notice any difference in concentration. Okay, conceptually, that's equilibrium. What we're going to do is apply some math to this, and that'll be the end of chapter 7. So there's an introduction to equilibrium. I think I have a video coming up, an external video that has some animations and things that I think will help. All right, I'll see you after that animation. We'll restart on page 7.20.